because he's supposed to be an AI? Is it's related? I mean,
Yeah, it's a combination of Salvador Dali, the
because of what it
famous
does.
artist, and then
Oh, I thought you
Wall-E,
said
like
Dolly, like the
It-
big-titted country singer.
No,
no, not Dolly Parton.
Salvador Dali.
It's DALL-E. So it's like the movie robot Wall-E, but with a D. And so it's a combination of Wall-E and Salvador Dali.
But they
painter.
don't get it confused. They actually had the inspiration for the name from Wally, is where they got it from.
And Salvador Dali.
Yes, and Salvador Dali, yes,
Yes.
for the first part of it.
That's what I was trying to say.
So what's it about? I'm not gonna it's gonna take me a while to read all this. So
Dali is just like one example. The article is basically just kind of giving the sort of difficulties that AI can encounter. Some of the things that we think are really easy. I guess to back up a step, a lot of people, we tend to think, oh, AI will be able to be even better than humans, or at least as good as humans. Like last week, we talked about the pastry AI that was pretty much just as good, or approximately just as good as humans at detecting cancers on microscope slide images. Whereas this is going into kind of all the stuff that we do a lot of calculation in our brains to do, that we kind of take for granted and see as like an easy thing to do, like reaching out and picking something up.
so we're
and
talking
it goes
about
into
motor skills here.
essentially, but it deals with
Comprehension.
So not necessarily
they break it up into like perception and like
There's
and
a
also
couple
the
categories.
locomotion and keeping those in tune with each other is actually a lot of calculation going on for us to be able to do that, to just be able to walk or pick up an object.
right, but we're talking about AI's ability to do like functions but robotics wise.
Yes, yeah. So it's
Okay.
a little different than the pastry AI thing we were talking about, where it's kind of just like a fancy checkout machine with a camera. This is like using cameras and robotic arms and things like that to do work, to do things. Even something as simple as like picking something up, it talks about a lot of different stuff. One of the interesting things I thought it talked about was like how it doesn't have common sense. Like we would know to grab a lollipop by the stick and not the candy part. Yeah. So yeah, just like common sense things that like we would know, like, and we also have learned to grab things with like what they call a robust grip. So if you have like a prism, you'd grab it by the flat sides and not like by the corner where it would slip off. Whereas like it's actually not very straightforward for a robot to learn that kind of thing, what a robust grip would be for its type of hand and for any type of object it might encounter.
So baby's not so dumb then, huh?
Exactly. Yeah.
That's
It talks
exactly
about
the point. Yes.
Yeah, it talks about how it takes a lot of work and we haven't even achieved it being equivalent to an 18-month-old baby's brain. Like we'd have no robots that are even that good. And we've seen like, have y'all seen like the Boston Dynamics robots, like the little yellow and black robot dogs and stuff that are like, look it up. You seriously, like go right now, look up the Boston Dynamics dogs. They've also got some like bipedal like robots that will do like parkour, I think. What? Super uncanny valley. Yeah, they'll do like flips and stuff. They're working on some crazy projects of some very advanced
What
robotics.
Did you call it? Boston what?
It's called Spot.
Dynamics.
Oh, Dynamics.
Yes, Spot.
Yeah, he's a yellow and black robotic dog.
Oh, okay. Yeah.
The first link is contact sales.
It does say that. Let's buy one.
Yeah.
There's a mute button.
But I mean, this is like a headless, four-legged thing. Like,
yeah, I was just bringing that up because it's a cool thing that you should definitely know about if you don't know about. and they definitely use a lot of AI. There's like videos of them going through like obstacle courses and like kind of warehouse type setups and doing stuff
Yeah.
like holding doors open for each other and stuff. It's pretty surreal. It's very like uncanny valley. They look
So
almost alive.
without actually playing like a video of watching this thing, does it like walk normally, or does it do like the little like hopping weirdness that
It doesn't hop. It
Not
does do
hopping.
like it like uses opposing legs to move, like you would imagine, like kind of like a dog would. It's obviously more mechanical, but it does use like alternating motions of its limbs to move in a very, in a way similar to
so
how
it tries to mimic
creatures.
normal, like how
Yeah.
we would perceive a dog moving, or how a dog does move.
Yeah, basically, yeah.
Wait, you can customize one? What? What are these for? Why are they selling them? What is going on here?
Well, because they've had a huge they've had a lot of publicity, so I'm sure there's a lot of people that are like, I want one.
5.4, huh? Yeah, now, the reason why that stands out to me is because, sorry to cut you off, the cameras that I just got are IP66, I think, rated. So I wonder, I haven't looked into it, but now I'm going to, the different ratings of the plastic.
For the dog?
Yeah, because they're
They're talking about
IP5, yeah, they're IP54, I think it was. And the cameras that I got are IP66.
Yeah. It all just, I don't know the different standards. I've seen those standards before, but I don't know what they mean offhand.
Yeah, I haven't
But,
looked into it either.
it's probably just whatever it needs to be good enough at. And, that's probably a fairly trivial thing to change the outside of.
Yeah.
The fact that these things can
It's
just
not
move
bulletproof.
around. But you could probably make one bulletproof. It'd probably be heavier though.
Yeah, we have like a war dog.
Yeah, for real. Like for all we know, the military already does use stuff like this.
Yeah,
Yeah, that's
strap
true.
a freaking machine gun to its thing's back and let it go.
Jeez.
I don't know if we should put that on the internet, but yeah.
Where's
No, yeah.
Cyberdyne when you need him? Oh, good
Hmm.
lord.
Yeah, I wonder what this whole missions thing is about.
Yeah, so a long way
missions,
from
expanded
stuff like
autonomous missions.
iRobot then, huh? The
Yeah.
Will Smith movie when they knew how to shake somebody's hand without ripping their arm off.
I would say
Yeah.
at this moment, yes, we are still a little bit far away from that, but
Yeah.
it also may be closer than we think too, because who knows how long it's actually going to take us to get that stuff down. It just is a matter of time, and how much time is the question.
Well, how much information are we giving? And this was the big difference between the pastry AI and deep box learning, or box deep, or whatever the hell you call it. The
Deep
black
learning
box
neural
thing. Yeah,
neural networks. Yeah.
Is that the neural networks were not giving it a whole lot of information. The pastry AI thing, we would be giving it a whole lot more information up front, and hence probably why it's easier for it, or quicker for it, with less examples to figure some of this stuff out than just going, here, box, figure it out.
So
How much
kinda goes
information are
back-
we giving these AI systems in human movement and control and everything? I mean, does it go into any of that, or?
It does, and they actually kind of talk about how they use a combined approach similar to the end of the story about the pastry AI last week. Like they use a bit of pre-programmed subroutines, but they could also use learning systems in AI. But the problem is that it's so vast, and there are things that we take for granted that our brains do that we wouldn't necessarily think, or even if we did think, it's just so much to think about. Like again with the common sense thing, they talk about how if you show an 18-month-old just objects moving along a path, and one takes an unnecessary jump over a pit to get to a path, that elicits shock or surprise on an 18-month-old's face. But that hint of, or that feeling of
The
surprise.
computer came up with that as a solution to a problem, even though it was
No.
unnecessary.
It's no. No. So they're using a video as an example to show an 18-month-old, and they're also showing this AI that 18-month-old. But the problem is an 18-month-old can pick out that this unnecessary jump is like a surprising thing. Like, why did it even need to do that? But an AI wouldn't necessarily know that that was an unnecessary jump. It doesn't understand what surprise is.
And then this kind of ties into the whole thing too, more to the point, which was what was surprised me about it is that they can program hundreds or even thousands of these pre-possible situations, explain to them why, give them the exact details of these 3 situations, give them a 4th situation that will only be because of the first 3 situations, and it would still guess it wrong. Somehow, some reason, it just doesn't, it's not able to put things together that we would think are common sense. Like, if there's not a pit, you don't have to jump, being the example.
Yeah, like there's just so much that our brains have kind of learned to handle and expect even. It kind of talks about how this AI, an AI might be able to detect distance. That's tough enough, but when it's seeing the walls and stuff, it doesn't necessarily know walls. It just knows an object, you know, and it might be able to navigate. And then another level above that is like, say it can navigate through rooms, but say it encounters a bathroom. A human might know that that bathroom is a dead end and doesn't need to investigate any further. But a robot might go into the bathroom and have to like learn everything about that bathroom before it can be like, okay, nothing further here, and then move on. We just know, oh, it's a toilet. There's obviously not going to be another door at the end of that room.
Well, they also don't obviously see the way that we do. I mean,
Sure.
I would figure that their vision kind of looks more like a
simulated world is,
well,
is how you
the
could
telemetry pictures you get from like Tesla and stuff with their self-driving crap, right? It would probably look very similar to that, like object recognition and whatnot.
Absolutely.
Well, again, it's data that's interpreted as what we tell it to interpret it as.
But they're using sensors that we're like familiar with how they work, like
Yeah.
video sensors and stuff like that. So
yeah,
they might not ever need to render it into actual video, and they can just use the digital signals, but it's still kind of the same thing. Yeah.
So we're just simply better or faster at it because we don't have to think about it.
We do think about it. We just don't realize how much processing
it
actually goes
happens
into that.
so quick that we don't think about it.
It's
that's
yeah,
the
it's
idea.
not I guess it's not even a conscious thought. Yeah. So in that sense, we don't think about it. It's like subconscious.
But wasn't the whole point of the neural network stuff is that it's supposed to function faster or think faster than we can?
Not necessarily. But you're kind of highlighting on an interesting thing, is that these AIs can be really good and specialized at certain like logical tasks, like recognizing things in images that might even be better than humans. We're still kind of toe in toe with that, but it's foreseeable that AIs can be even better than humans at that. But here's an area where they just trip, pun intended, they trip left and right.
Throw something unexpected and it can't compensate.
Yeah, and it's
big part of it.
They're trying to describe all these ideas of like higher level things that our brains do that we kind of take for granted. That
understanding our place in space is a big thing. Like, I mean, being able to grab something is not only where you are, but where it is, what force you are going to apply to it, what force it is going to apply to you. Even if you don't know physics, your body knows that. Your body knows that when you touch this, it's going to have this reaction.
Mm-hmm, exactly.
So you compensate, you grab it a certain way, you put pressure in a very certain precise way. And those simple calculations, or maybe not simple, maybe I'm using the wrong term there, but those calculations our brain does, and we don't realize it. We don't know how it does it. It just does it. It's common sense to us.
You brought up something right there, Joe, that like we have sensation. Like I don't know if robots have, well, I mean, I would assume that they don't. Like a robot hand doesn't have what do you call it? Like it can't feel, well, I guess it could.
They do
put pads on there, like it
they
can
do
feel
have
pressure and temperature and stuff, but
yeah,
but texture and like as far as like grip and everything,
it's a
You know,
lot
like
harder to
whether
do.
a object is smooth or, is grainy or
Combining all these things is very, very tough. I will agree
They,
with you on that. I
an
mean,
example they
having a hand developed as we have with the skin and the nerves and the blood and everything that we have working, kind
it
of
do-
unique,
yeah, but
in my
is the
opinion.
skin and the blood and the nerves necessary, or can we have sensors that do the same things electronically?
they are working on that. Yeah, getting it down to the same resolution of a human. I mean, it might not even be necessary to have that level of
Right.
detail to hold an egg.
Yeah.
Humans are amazing. We can detect like a sheet of paper like underneath another sheet of paper. Like a very small like
Oh yeah,
thing we
like
can actually
when you're
detect.
turning pages in a book and you're like, oh shit, I went two instead of one.
Yeah, you
Mhm.
can
So
feel it.
yeah.
Yeah. Another thing that the article kind of goes into briefly that relates to what Joe was talking about, like it talks about how they've studied mice visual systems and how it seems like they have the ability to like their visual system is active in the womb. So they're kind of learning and able to kind of see in their mind's eye before they're ever even born, so that when they are born, they're ready to go right off the bat, which is just really interesting.
And a lot of organic beings, if you will, have that. Like,
Well, mice, let me throw that out there. We're really closely related to mice.
yeah,
So that kind of thing is not a far-fetched to say, like our brains are probably pretty similar. Individual drug interactions can differ widely for mice versus humans, and so it's good to be skeptical in that case. But this is a very general, like mice have pretty similar brains in the general sense that this would be like in the raw workings of their visual system. It's kind of similar to ours, kind of like how the pastry AI can use its visual processing parts to do cancer research, but also pastry
Is no one
research.
yeah.
comparing humans to chimpanzees anymore? Like,
Well, we compare humans to a
We
lot, always. Sorry, but
people definitely do. It's something we can talk about that. I think it's a little bit overused, and there can be a lot of misconceptions when that gets brought up. The whole like we are 98% similarly related DNA wise to chimp.
well, I mean,
It's
yeah, I mean, I don't necessarily care about all that, but like that's been the comparison like for the longest time. And then you were just talking about mice, and I'm just like, oh,
Well, mice are a lot easier to study in a lab for a lot of reasons, and so
size.
their size,
We
how
can
quickly they
produce them
reproduce.
easily. Yeah.
It's called a model organism, and there's a
Lab
lot. Even
rat.
chimpanzees have a model organism kind of thing, but like
but what
mice and
is
rats are.
like even for other stuff like pigs, right? Like I know
Mhm,
I tend to bring him up every freaking episode, but um Elon Musk's Neuralink, right?
mhm.
Like they were testing that on pigs, like the putting the wires in the brain or whatever and cutting out the piece of the scalp and whatever, or the skull. But
I'm
yeah, they
pretty
were
sure it was
I
a
want to take cite
dead
your source.
decapitated pig head, but yeah.
no, they were live pigs. They had
Was there one
there's
on live
three
pig?
of them.
I remember maybe I'm mixing up a different thing. There was like, maybe it wasn't, I thought it was Elon Musk's Neuralink thing that they hooked up to a dead pig brain and were able to detect brain signals. That's the whole thing I
No,
don't want to get into.
Yeah,
they
that's
did it on
a
live pigs and they were getting information and stuff. And then that was one I guess they had I don't know if it was a presentation or something, but they brought the pigs out, they had them in pens and they had everybody on the team like talking about, what they were trying to do and accomplish and everything. And I don't know if it was just basically to see if the surgery would work or if they could get the little I mean, these wires are like much smaller than like human hair. I forget what
probably,
the heck
yeah,
they were, but
microns thin. Yeah.
Yeah,
yeah,
nanowires.
yeah. But and then they had showing like the pigs were like, I guess for the animal people or whatever, like that they were still fine and alive and doing well and whatever. They had them out
PETA.
there. But then it was the next time, like they tried to put the chip thing in a chimpanzee, right? That was like the next step, I guess, later on. And they had the chimpanzee was playing pong with his brain on a TV. And
Yeah.
then that was like I kind of lost touch with it after that because one of the guys like quit for some reason after they did that. And I don't know I don't know the whole story and what that, but one of the project leads like quit or something shortly after that chimpanzee thing came around. So I don't know what that was all about, but yeah, they definitely did pigs, and I never understood why they did pigs. I'm just like, okay.
Pigs are actually really similar in a lot of ways to humans.
To humans, yeah. I get
Because, well, I can explain why.
please.
Like part of it is their size. Their size and weight and all kind of distribution is actually kind of similar to ours. Their anatomy, internal anatomy shape-wise is actually kind of similar to ours. And even down to like the proteins on their tissues, like on like their organs and stuff, are pretty similar to ours. For being further, more distantly related than like a chimp, it's remarkably similar, and they're really easy to access. Pigs are easier to access than chimps for the most part.
Well, I mean, they did. I mean, what you were saying with the organs and stuff makes sense, because weren't they using like pig organs or something to replace with like, in lieu of like human stuff? Or
they use pig valves occasionally, and they I think I saw something recently about a pig heart, like a full heart pig heart transplant that they like. I don't know the full details on that, but there was something like that recently. Yeah.
But so yeah, we're a lot like a lot of other animals, apparently.
Yeah, which makes perfect sense. I mean, we share a lot of DNA with a lot of different
why
creatures
can't
on
we
the
be
planet,
more like birds?
if not all of them, I think.
If
That's
we
what
were
I'm
more
saying.
like birds, we would be more related to dinosaurs, and I would just be happier.
It's true, but then people would be trying to eat us for like holidays and shit.
You just have to eat them first.
Eat the people.
Still technically cannibalism, people.
I mean,
not if you're a
that's
bird.
the world you live in. You would know no different.
But then everybody
that's
would
all
be
I
a
gotta
bird.
say. I mean,
oh, we're talking about bird people now.
No.
Well, then why does everybody have to be a bird if you want to be a bird?
Well, I'm not saying that. I said it would be cooler if we were more related to birds, people as a whole. So if you were like, you wouldn't eat turkey anymore if that was a thing, because then everybody would just, it'd be cannibalism.
It'd be like
cannibalism.
It'd be like eating chimpanzees, kind of what you're saying.
We don't do that, to my knowledge.
well,
most people don't.
I'm sure they do somewhere, but
yeah.
I don't eat chimpanzees.
There's got to be a distinction between a chimpanzee and a monkey, because I know in some countries, like with the monkey brain stuff or whatever, I know that's a thing, people eat that, but like, yeah, chimpanzees though, like, I don't know, I've never heard of it. So then again, I live in the US, so yeah.
Like there are monkeys and there are apes. Monkey, and they are related. Like
they're all classified as primates, right?
Yeah, which we are too. Yeah.
Yes.
And then there are like New World monkeys and Old World monkeys. We can talk about monkeys if you want.
I was like, so definitely getting sidetracked here. That's not, yeah. I don't know what path I was going down there, but let's
you have back up a major point here?
So, but yeah, so that's just what they were going on. Like, it was just the fact that on the robotics side of it, that AI is having a hard time trying to be us, I guess.
Yeah. There's more than just the grabbing stuff. There's the ability to comprehend what somebody else is talking about. Like, what understanding a person is what they say it is. So if we were to talk to an AI, a lot of times it doesn't understand you really.
I don't know. Alexa understands me pretty good.
It has something to do with bits, though.
She gets me wrong all the time. I don't have Alexa. I have I don't want to say the word because it'll activate the G word. But yeah. Oh, well. Yeah, like the example that Joe's talking about, they talk about that DALL-E thing, and it like you can like type in a description of something and it'll try to make images based off of your like plain text written description of a thing. And
you could this is without teaching it anything, or we just like, are we teaching this anything? Or
it's been taught language.
Yeah.
Okay. Like there are different ways of like teaching language and different levels of it. There's like a common technology called GPT-3, which is like the most common like
they use
gold standard currently being used for language processing kind of thing, and it can process everything from individual characters in words to like fragments of sentences, and like understand kind of the trends going on in sentences. And it's fascinating how in depth it's gotten. But
And
yeah,
I
it
looked
can
at I'm
kind of
sorry.
understand people. That was all I was going to say.
I looked at some of the examples of some of the art that it did, and it amazed me at how many different examples it could give you. I'm wondering if they have many different versions of it that give you an example because of the similarities in so many of them when you go from one example to the next. Different subsets of information, by the way, like different tasks, if you will. But more to the point, like a lot of them were incorrect. Like the one specifically that I noticed was about the this block, then this block, then this block, and it had like filler sentences kind of. So it almost like it was provided unnecessary information. And it's like I immediately understand, okay, one block here that's red, this block here that's this, and this block here is this. You tell me to draw that, even with all that information that it gave me, I could accurately draw that. Even a child could probably accurately draw that. And a lot of times it got it wrong. It did the best that it could, but it got it wrong. And I was kind of amazed at that too. But that's the understanding what we mean. It's easy for somebody else to kind of interpret, okay, they want 3 blocks, these colors in this order. It's still hard for it to interpret that level of information with a sentence.
So it's not
Yeah.
necessarily just listening, it's comprehension.
I mean, on some level, yeah.
What is the block example you're talking about exactly, Joe? I don't know if I fully understood what you meant by that.
Hold on. Maybe it's on their actual site. Okay, because like I said, I dove into that DALL-E part a little bit more. So on their actual site, they provide a link in that article. Small red block sitting on a large green block. That one they got right. That's not the one. It's the next one. Sorry. All right. Stack of 3 cubes, period. A red cube is on the top, comma, sitting on a green cube, period. The green cube is in the middle, comma, sitting on a blue cube, period. The blue cube is on the bottom. Okay, so it gives you basically the number of cubes, the first cube on the top, the color, and what it's sitting on. What it's sitting on, basically the color that it's in the middle, and what it's sitting on, and its color. And then it reiterates what the bottom one is and its color. And in a lot of these examples, it got it wrong. In a lot of them, it got it right too. But a lot of them, it got it wrong, and it's almost, hard to understand why it got them wrong, in my opinion. Because that, to me, would be a very simple thing.
It was the commas.
When you say you don't know why it got it wrong, you want to understand like what's going on in the logic you think it's using to get that?
Yeah, I mean, like in one of these images, just for example, it has a red, a blue, a red, and a blue. You wonder how it got to that solution.
Yeah, so the problem with these kinds of like neural networks and these kinds of AI systems where they use learning is that they are the black boxes that Rob likes to talk about all the time. And so we can't know. It might not even be that it's using what we might use to make our decision processes, and it's almost certainly not interpreting the language the same way you and I would. And you and I might interpret that sentence slightly differently, but probably a lot more similarly than the differences between all these images, as you're pointing out, because it gets some totally wrong. There aren't even red blocks in the images. So it's like it totally missed that, or red cubes.
I'm actually curious now. You kind of brought up a thought to me. You said me and you would probably get that right. I wonder if you tested as many people as it did examples of this, what the ratio of right to wrong would be. Do you understand what I'm saying there?
You're saying if you use this test on people, how would they?
Yeah, give them the same exact sentence and say, do this.
I mean,
how
I
many
think
people
it's
would get it wrong and how many people wouldn't?
I think
I'm
it's fair to
curious.
say.
I don't know.
I think it's fair to say any like what would be considered like a normally functioning adult, anybody would be able to get that could speak English in this case, or you translate it to their language. I think
An
anybody
equivalent example. Yeah.
could get it. It's like those word riddles, like it takes a little bit of processing, you know, like you have to do some thinking as you're reading it. It's kind of like those puzzles where it's like Sally is 10 years older than Larry and Larry is 20 years older than Charlie. How old is whatever, you know?
So
it's
then
like, it sounds.
here's my next question. Let's go younger then. I want to see if I give this to Taylor and see what she does with that.
Yeah,
And you should give it to your kids and see what they do with that. I'm very curious to know what will come of that.
Well, yeah, I was gonna kind of bring up. I was like, I'm wondering if like there's like a time like experiment or something that could be like, you know, switch on the robot and, you know, have a
Let it go.
newborn kid. Like I know it's impossible, but like, and give them both the same task and see who does it quicker. Like,
I
I mean,
don't know if
it
that's
could literally take years, but
that's a hard comparison to make, and it feels arbitrary to me, because where at what point do you start the timer? Do you start it after the AI has already done all of its learning, or do you start the timer as soon as the baby has been conceived in the womb? You know what I mean? Like where do you start the timer for where's the beginning there for the learning of both of those systems?
that's what I said.
Yeah.
It's kind of impossible
Valid
to do.
point.
But
Yeah.
yeah.
So my theory is though is that we've given this thing a ton of information, years worth of learning probably. I mean I'm sure it knows what a red block is, what a green block is, what a blue block is. I mean, it gets that
Well,
right in most cases.
I want to stop you right there. It probably doesn't in the way that we do. Like, it probably knows the word that is the letters R-E-D, and it knows the word that are the letters C-U-B-E, but it has no common sense interpretation of what a cube is or what it means to be red. Or even it would be hard for it to understand the joke between how something can be red, the color, or red, like
as in a book.
Like you read a book. Like, it would be, you could program that in there, you could teach it to learn that, but like that's just going back to the common sense aspect, where like you'd have to like program all that in, and it feels unnecessary, but that's just to highlight how different we are from these things, these systems. And it doesn't interpret things the way we do, as much as we might want to try to anthropomorphize these things.
I think you actually provided the answer right there that I was kind of going for there, I guess, is that it's what are you going to design it to do? What do you want to do? Do you want it to be an all-inclusive AI that really does know everything and can do everything, or do you want it to do a certain task?
Yeah.
What data set are you going to give it? How long are you going to give it to learn? What do you want it to do in the end? That's the ultimate goal of AI, is to do what you want it to do. So
Yeah, but is this like, you know, outside of like the language issues, I guess, and understanding and common sense? Oh, okay, definitely common sense. Like if you told one of these AIs to walk across the room, pick up something, pick up a basket, and walk back to where it came from, you know, and you had it repeat this day after day after day, and then, you know, now you know, one day you decide to open up a hole in the floor. Does it know to go around the hole? Or is it just going to walk the same path it's been walking, fall in the hole?
Yeah, I mean, the answer is obviously it depends, you know.
Yeah.
But yeah, you would have that's a good point. That's a contention you would have to prepare for, even though it's really rare, probably would never happen. But it's like, what if, you know, how would it respond to that situation? It has no creativity to handle a new situation that it's never encountered before. Whereas we
I think
do.
you highlighted that right there. There's
any
no
child. I mean,
unless you program it for something, it's not going to know to do something. Is the point?
Well, but it's supposed to be learning is the thing. I mean, it's like you can't.
So you'd have to give it a hole multiple times so it can learn.
Right, but you can't like prepare it for every possible situation and make in a structured environment. Yeah, sure, but you know, I mean, what's the point of artificial intelligence, you know, if it's not intelligent? I mean, any kid at a given age or whatever, like Brett, for instance, would not like go and just willy-nilly fall into the freaking hole. they would stop.
To take it another level, even if it could recognize the whole, it wouldn't necessarily know that that's a weird or novel thing, whereas humans would. Like the article that we're talking about, it kind of mentions how humans know to expect doors and windows to be on the walls and almost never on the floors or ceilings. And that would be weird. And that kind of goes into that feeling of surprise and knowing if something is off. Like we do a lot of calculation to be able to detect that. And we make a lot of assumptions that might not be made in a system like that, because it might seem like banal or unoriginal.
Learn that over time, though. Yeah. Like when we're newborns or whatever, we don't know where a window is supposed to be.
No,
over time, we learn that this is where we find them.
Yeah, it's true.
When you're a newborn, you also don't know what a window is. I mean,
Right.
to be fair, you know, you could teach a computer what a window is. It still doesn't mean it knows that it's supposed to be on a wall. You have to teach it that it's supposed to be on a wall too. You know, it's all data sets, and it's hard for them to continually understand that's pretty much the only place where they will be, though. You know, it's still going to look for them everywhere to determine that there is not one there, because it has to satisfy the not thing, in my opinion. That's what it's doing. It's saying, oh yeah, I have to make sure that there's not a window on this floor to verify that there's not a window on the floor.
I mean,
period.
You're talking about taking robotics from where it's just a programmed thing, like in a factory, which they do very well at, and basically going like, you know, having an Amazon delivery robot that's all like, you know, you hand it a package, you go, here, take it down the street to this address. Now, you don't know what they're going to run into as they walk down the street, so they got to figure that shit out. But I kind of figure that's the whole point of just general computers, and then the difference in AI anyway is that it's supposed to be able to figure this shit out.
Yeah.
Otherwise, what's the point?
I'm glad you brought up the term general, because that's a term commonly used with AI, that there is general AI, and then there are like expert systems and like more specific iterations of AI that are really good at like a thing, like identifying pastries or some shit. But then there are like the general AIs that are ideally they could, I mean, you kind of have to define that. And people that are scientists in AI have a very specific definition of general AI, but like, how general do you get? You know, you could push that envelope a bit and be like, well, what does it really mean to be general? Does it mean you can Google things really well? Or does it mean like you can actually respond to the world? Does it mean you can actually understand humor and make jokes? You know, like what level does it really become general? You know, you kind of have to draw the line somewhere. It's never going to be fully the same as a human.
That I've always had. What is normal?
Robin Williams did a movie on just normal. That. So, I mean, Bicentennial Man. No,
I saw it years ago.
Yeah.
Barely remember it. Yeah.
Robot kind of gaining consciousness.
Well, I mean, it was a robot, and then the owner, like, you know, tried to teach it to be more human and stuff. And I guess like it eventually developed like the concept of humor and like timing with jokes and like when it's appropriate to say things. And then eventually throughout the movie, as time goes on, like he's like skin and stuff. He's basically becoming human. So it's like he's being like, you know, he gets like artificial organs and stuff to basically become human. I mean, I don't remember really if the movie was all that great or not. Like, I just remember that was kind of the gist of it. Was, you know, AI going from, you know, blank emotionless machine to, you know, crying in the end of the damn movie. And it's like, all right, we get like tear glands in a freaking robot, but or even the iRobot type stuff, you know, where these things could interact it with, you know, normal people in the world and function fine, as long as, you know, none of them went crazy and were, you know, attacked by a virus or whatever.
I imagine an AI on those levels are going to be comprised of a lot of different AIs, a lot of specialized AIs working together.
Whenever they figure
that's already kind of what they are.
You know, just like the dog, it's going to be a military application and eventually Cyberdyne. So yeah, you know, Skynet. It's great.
Yeah.
I'll say it's not possible, but
I mean, I don't know if we can do the time travel part, but
Not
Maybe.
yet.
Yeah.
Computers might figure that out. You never know.
Yeah, maybe an AI will figure it out.
The guy I like to bring up a lot, he happens to have a very big fear of this. So everyone's like, "Oh no, that can't happen." Okay, I don't know.
I wouldn't say it can't happen, but
yeah. Anyway, I never introduced the show, and I'm not going to. This is technically incorrect, and if you didn't know that by now, what are you still doing here?
Just like edit
Glad
that
to
part
have
into the
you
beginning.
Yeah, that's fine. I'll just put that in the beginning. It's no big deal.
yeah.
Don't even know.
So other one, oh, I don't want to just jump off this. Anyone have anything else with the AI thing? No. Okay.
Yeah.
So DNA data storage.
Yeah, I want to know what your guys' thoughts are on this.
This is not the first time I've heard of this, although I do think that this was really neat, like coming out of Georgia Tech here in Atlanta.
Cool, but very
this kind of next step to it. But I mean, this has been around since like I don't know. I want to say
it has a very specific use right now, and that's kind of the problem, because
I mean, it started back in like the 80s or something, didn't it? And then like with not actual like data, like computer data storage thing, but
yeah, it was
like the concept of it.
DNA is data.
Yeah.
I mean, that's all
Right.
it is.
But the I think it was back in like 2000s or something. Maybe it was like the first like recorded or where they actually put like normal data. I mean, I could be totally wrong, but I can't remember.
I don't know for sure.
Yeah, you're totally
it's
right.
Been around for a minute. This thing.
Yeah, the concept is not new at all.
Yeah.
Yeah.
But we're basically growing synthetic DNA to store data on.
Yeah.
Like yeah.
But like digital data, to be clear. So like taking the ones and zeros of a signal from a computer, it could be ones and zeros that encode plain text, you know, like a sentence, and putting that information, using it to then encode or synthesize a strand of DNA with the proper A's, T's, C's, and G's to revert it back into those ones and zeros.
Yeah.
Yes.
So now we have four parameters that we can assign things to instead of just the ones and zeros. Whatever.
Yeah.
But very interesting a comment I read in that article that was said internet in a shoebox.
Yeah, that was amazing.
Like we could fit all the information that's on the internet into the size of a shoebox. All these things that we have massive like server data farms and stuff for in the size of a shoebox.
I'm not sure how accurate that is, but that's a good analogy nonetheless.
What is your contention, Joe?
I don't know that A, it would take as much space as a shoebox, or B, that it wouldn't take more. I don't know.
It might
that.
actually take less.
I'd show your work. That's what I would say.
Well, like, so, but what is your exact? You don't know if it would be more, way less, or way more. It could be way smaller than a shoebox, or it could be way bigger.
That's just an analogy, in my opinion. That has no kind of basis whatsoever.
What was the one they said what were they fitting into a cube of sugar? Something this
every single movie ever produced.
Yeah, every single movie. Yeah.
And so it's talking about it's talking about information density there. How much can be stored in a square centimeter / cubic centimeter? They use square centimeters in the paper.
I wonder how many millions of gigs all the movies in the world are.
They mentioned
like
that
I don't even have
millions of gigs. No, I don't think we're. Yeah, they did mention it.
I didn't see that in the article.
No, it was in there. It was some weird number.
Yeah, like those. I didn't commit those to memory because I don't find them that important. Like they're neat and all, but like you could come up with any random, like, so I came up with one. How many, you maybe have heard this before, but if you took your DNA from one of your cells, do you know about how long, if you were to stretch it all out into like a single line, do you know how long that would be?
I've heard it before, but that's one of those things that I didn't commit to memory.
Nope.
That's fair. I just wanted to know if you had any guesses.
One strand of DNA?
One cell's worth of DNA, which has your
Oh,
whole
one
genome in
actual
it.
cell.
So it's your whole genome, but only one cell's worth of your whole genome.
I'm gonna go way out there. Maybe I'm wrong one way or the other, but I'd say 10 times around the Earth. Who knows?
No, not that big.
Okay.
So
I have
one,
no idea. Like, that's what I'm saying. I have no
well,
idea.
well, we can get that to that point if you want to, but basically, so one cell would be 6 meters, or not 6 meters, 6 feet, about a meter, or about 2 meters. Sorry. The confusion is basically you get half your genome from your mom, half your genome from your dad. So basically, half of that is from your mom, half that's from your dad, approximately. So about 3 feet of genetic information from mom, about 3 feet from dad. And that's in one cell. If you took all of your cells and stretched all of that DNA, it was like it could circle, I don't know, it was like it could go from the earth to the sun and back like 100 times or some redonkulous like that. Yeah.
Redonkulous. I love it.
But yeah, so basically the human genome is like 6 billion base pairs or nucleotides. So that many A's, T's, C's, and G's. In a single foot, that would be about a billion. There's like I did a little calculation. There's like 900 million or about a billion nucleotides in a foot. If you could have like a foot-long ruler, that's how many bits, if you will, would span that length. But the thing is, it's a single molecule, so it's really small. So that would compact up into a very small container, the size of our cell, actually the nucleus in the cell. So a very small container can fit 6 feet worth of genetic information, and that's like billions of bits. So I kind of trust the calculations that are like, without doing them myself, that are saying like it could fit all the movies. Like that seems reasonable.
That was actually in the article, not a
Yeah.
comment on the article by somebody who knows nothing about what they're talking about.
I think Rob was just saying a comment made in the article. I know I thought you meant like a comment to the article as well, but I think you just meant like a piece of information in the article.
You guys might be looking at a different article that I'm reading, because it said nothing
Cuba
about how
sugar
much
thing,
movies
like,
space is, and the Cuba sugar thing. Yeah, that's there, but
wait.
Scientists have said that if formatted in DNA, every movie ever could fit inside a volume smaller than a sugar cube. The internet thing, I saw the internet thing too, but I don't think it's in this article. That might have been in a different article.
I branched out.
I saw,
and see, that is exactly what I'm saying. I want to see show your work. That's what that was my whole point. My point wasn't that that person is wrong. My point is that I have no idea what their basis was, and you guys apparently have read this somewhere. So
yeah, that was either something I moved on to after the initial article or something that I had read before in some other thing. But yeah, Internet in a Shoebox was definitely something I read in an article.
I'm pretty sure I
DNA
read
data storage.
I'm pretty sure I read the same thing that you did.
Yeah.
I kind of take it for granted because like I don't take issue with that. It seems pretty believable to me. I totally respect your skepticism on this.
Yeah, and I wouldn't say it's impossible either. I'm just saying, I don't know. It sounds like it could work. Yeah.
Well, let's go with what you're saying. Like they are basically taking how dense it can get and then expounding that outwardly as if it was like a big gumball, you know. But obviously there's a like logistics problem there. That's not how they're doing it. They're using like chips on, you know, little grid arrays and chips, and those take up space, you know. It'd be like if we talked about computer chips like CPUs as just being like a ball of transistors. Obviously, that's not what it is. They have to lay them out, and that takes space too. So you're right. Like it would probably be, if you actually wanted to like effectively store all that information, it would probably be bigger than what they're estimating. But the DNA could ball up that to
DNA
that small
itself, just the DNA, not all the other equipment and stuff that would be necessary.
So not even that. It's not like DNA and no empty space. They're probably going off of the density that they got in these tests that this paper is about, because that's what this big article, this big finding is about, is that they got really high density of information. Basically, they got a lot of wells packed in this little chip, a lot of little tiny cylinders packed in this chip where they can do a lot of single strand syntheses at the same time and have a lot of information in a small amount of space. That's kind of the bragging point that they're making here.
The other thing I found interesting about this technology is that as far as sustainability, it's great. I mean, they already use it for like time capsule stuff or whatever.
Well, you have to keep the information very, very cold, from what I understand.
Oh yeah, I mean, technically it lasts forever. It's not like I don't really know about technology like phasing out, but they did mention that, probably not in this, but in something else I had read, that it's always, we're always going to have a way to access it. So it's not like, when we started out with, like punch cards and stuff and like old Tandy computers to the solid state drives and RAM and stuff that we have now. It's like technology is always changing. So you can't go back. Like you would be really hard pressed to find a machine that can run a disk that, from the 80s or something,
Yeah. Even
like, yeah.
I thought the same thing. Like the USB plug standard probably won't be the standard in 100, 150 years, but DNA will still be around because we are made of DNA, and we will always, as living creatures, have an interest in DNA and dealing with it. And right now, our like ability to synthesize and read the DNA it's gotten a lot cheaper just in the past 10 years. It's still a bit expensive to do it like conventionally, but it's, like I said, it's gotten a lot better just in the past 5-10 years, and it's only going to be continually improving. Yeah,
especially if we continue reaching that area. I mean,
which we're made of DNA, so why wouldn't we?
Yeah, that's what one of the articles was getting at, is it's never going to disappear. We're always going to have a way to read it because we're made of it. So
well, now that we have the ability to read it, yes.
And cold is the best way. They are studying other ways, like chemicals you can add, like buffers and things like that. Cold and dark is probably the best way. Yeah. Because the studies that I've seen that have tested those other methods tend to find there's not much difference between them. But the thing we definitely know is cold is how you avoid the decomposition of the DNA polymer. Yeah.
And then there's, I mean, I don't know exactly how true it is, but there's been points made to where if you do keep that cold and dark thing going, that this stuff is not going to degrade or like it'll literally last forever. So
forever, I don't like the word forever. Yeah. So like the evidence we have, I think the oldest thing that we've been able to get DNA from was like 700,000 years ago. So we have that as like kind of a proof of concept, as like a bit of evidence for it could probably be at least that long, that the DNA could last. Now there's issues with that though too, because it's not going to be fully intact in 700,000 years. There will have been a lot of changes that happened.
There's also so you need issues to deal with the coding sequence too, or whatever, that has caused problems, I'm assuming, because it doesn't, like with drives and stuff now, like the way it is, like if you have a bad sector or a bad spot, it's just a bad spot.
Talking about the error.
What they were saying about the DNA is that you have a bad spot and then now it's all together. Like there's no, it means completely something. If you have a bad spot in the DNA, like it's just going to like admit it or delete it or something. And it's just going to combine on top of that to where now it will read as something completely different when you go to decode it again.
They're working on the error correction.
So there's a lot to talk about and kind of unpack there, because there's a lot of error rates in almost every step of the process for the DNA stuff, but also for magnetic storage, like you kind of you guys are saying. There are error correction methods and all that, and there are ways of doing that with DNA as well. Some of it is in having a bunch of copies. It's like physical redundancy. You can have a lot of copies of the same piece of information, and that's actually how we do like whole genome sequencing in the lab nowadays. You don't sequence the whole genome in one strand. It doesn't work that way. You make a bunch of copies of parts of it, and then there will be like overlapping regions that you'll use a computer to like lay all that out, and they call that coverage. And the more times one area of the information, the sequence got read, the more coverage you have and the more confidence you can have that that's the right result. Because sometimes you might have coverage of like, you might have coverage of like 10, which is actually pretty low, but say you have like 10 reads of that part of the sequence, 2 of them have a G in that spot and the other 8 have a C, you can be pretty sure that the 2 Gs are the error and the C is the actual useful information.
Right.
Yeah.
But again, like that's, yeah, and having copies upon copies, yeah, that's probably the biggest way to prevent the data loss or data misreading, I guess. But
it's
like there was something with the article saying where we're back in the day when CDs were still a thing, you know. Again, I know you hate the term forever, so I'll just say plastic lasts a really long time.
But the film on it doesn't, and that's what
Right.
has the pits.
Well, and then they said it's like, okay, but yeah, until you freaking scratch one.
Yeah.
But
and they do have
that was kind of like the permanent storage idea or whatever, and it's still, I mean, I would probably say it's still, if you keep it well protected,
Comparable to
I'm assuming
else.
it's probably going to last longer than flash memory stuff today, considering how volatile that stuff is. But again, not really, what do you call it? Not a whole lot of space on a CD compared to some of the other stuff that we have now, obviously.
Well, that technology
again,
improved.
Even with magnetic drives, you have, like I said, if you have a bad sector, it is just a bad sector. It's still there. It's just not readable. So you have the rest of it. With the DNA stuff, if you have your TCGG, whatever, and one of those G's is bad, now you have TCGT, because that bad thing is gone, and now it means completely something else.
But that can,
again, having the copies or whatever, like you were saying, one way to prevent
what
that.
it's supposed to be, how long
that can happen in magnetic storage too, especially if you don't have, like if you keep one powered down for years without any power running through it, it can't do that error correction. And so some of those bits might change without the ability to have recorrected those. And so you could have permanent changes to the data that corrupt.
But I mean, even in corrupted drives, it's like you can still pull some of it, if not all of it, but at least you know what you're getting is what it was. Like the stuff that you are getting, you know, is still what was on that drive. Now, with the DNA stuff, from my understanding of it, and again, probably totally wrong. I'm not a what's the archaeogenetics? Yeah, archaeogenetics, I think was the, I don't know, whatever. What was I saying? Oh yeah. You might get the information off it and it might be the wrong information and you may not know it.
So instead of a picture of a cat, you'd end up with a picture of a dog?
But that's true if you tried.
Strokes, yeah.
I don't see how that's different than a magnetic drive in that case. Like magnetic drives only last a couple of decades before they start. Right. And you might be able to get some information, but that's kind of the same thing. If the DNA goes corrupt, you still would get a lot. You could get a lot of information, but not all of it.
But would you be able to piece it together? Like if you have, say, this is going to be a really simple ass example, but if you have a picture of a alligator and a horse and a dog, right, on a drive, and the sector with the dog is corrupt, you still might be able to pull the alligator and the horse off of it. But with the DNA stuff, with it just being deleted and it just going back together, you might have a frog now. It may not even be what it used to be.
But if you don't keep it powered on, you might not have any of that. It might be all
situationally.
It might be too corrupt. Yes.
Yeah.
Yeah.
So I think that's kind of what you guys are going back and forth with is what can be retrieved, if anything, versus how long it is. And really what it comes down to is when you're talking about like an image on a hard drive versus an image stored as DNA, if you take a part of what's the information that's stored on a hard drive, you might still be able to determine that's an image and make most of the image out. Can you do the same thing with a piece of DNA? I think that's the question. If it's an image of a
rewriting
horse,
the sequence,
would it be an image of a horse, or would it be now a race car? Like not even a picture. It's a race car. You know, I mean, what does the change or the error in DNA do to the rest of the information?
So I just want to say, like, for the magnetic storage, it's not a matter of if, it's a matter of when. It will eventually all the data will eventually
Well,
become
right, yeah.
garbage
I don't think
over
we're
time.
talking about that though.
Yeah, we're
We're
not.
just talking about
That's
the
not what I was
error
getting at.
and
Yeah.
stuff, not the length of
The-
time that it lasts. We're
but
talking
that's
about
because of
error.
errors that accumulate over time. Like
But
that's
even-
because of cosmic rays and things like that
But
striking the
even in a drive that's like 6 months old, okay, like you don't expect a magnetic drive to go bad, but they can get bad sectors, whatever, great. But what happens to that information that like it doesn't come? The ones and zeros don't disappear. You just
But-
can't read them. There's still a hole in the data chain. With the DNA stuff, it just disappears.
So you're talking about if in both cases, if there's one bit wrong in the magnetic storage and there's one bit wrong,
Or multiple stuff, yes.
but that's
yeah.
that's
Yeah.
like why I was going to the extent of like
I
DNA
don't
is
know.
good
I
because
don't know
it's
enough about it to really to really know how it works, like how a single bad sector or a single bad what are we calling them, the chromosomes, something, whatever, I don't know, with the DNA.
So like a bit for DNA, the analog to a bit would be a nucleotide.
Nucleotide, okay.
You could call
So
it a base.
one bad nucleotide that literally is just gone now because it's bad, and they don't just sit there anymore, right? I mean, that's not how DNA works. Well, I don't know, it might be because but
Like
that's not my understanding of how it works. Like if something goes wrong with a G, then they're just going to merge.
so
Like,
that's
the
what I
G
was
is never
alluding
gonna be
to.
there.
That's what I was talking about when I was talking about coverage. So when I was talking about how there might be, you might have your sequence, say your master sequence of your information that is just one sequence, but when it comes to putting that into DNA, you're not going to have just one strand of DNA for that sequence. You're going to have a bunch of strands of different pieces of that file or image or sentence of text. You're going to break that up into different pieces and have not just one copy of those pieces, but you'll have like a cascade of like overlapping regions that will have a lot of redundancies. So
Similar to
basically,
striped raids.
I don't know.
What was that, Joe?
Similar to a striped raid in a computer. How
I
they
don't know what
have,
that is.
you know what a RAID is in a computer with hard drives? What a
No.
striped RAID is? You really don't know? I mean, I'm serious. Like, I'm surprised that you don't know what a RAID is.
I mean, you're
Do
not
you not
describing
know
it,
what a
so I
RAID is,
might, but
Rob?
you're just saying you don't know what a RAID is and you're not saying anything. Like, I might,
It's a
but you're not.
storage. It's a way of doing hard drives as storage in a computer for redundancy and reliability and access speed. And
No, yeah, I don't really know much about
wow,
that.
Rob, you don't know what I mean when I say a RAID in a computer?
Why are you saying
No.
it like that? Like,
Because it's actually a very common thing, especially in people who are tech people. I consider you both to be tech people. I'm surprised
okay.
you don't know what a RAID is. A RAID 0, a RAID 1. You
I
guys
don't know
don't
why
know
you're
what
being
those
so
are.
harsh about this, Joe.
I'm not being
Like,
harsh. I'm surprised.
you are.
I'm surprised. I'm
But
very surprised.
You're like exclaiming pretty emphatically how surprised you are, and like
It's that
I'm not.
surprising to me that you guys don't know what it is. I mean, what else do you want me to say? I'm not trying to be insulting. I'm
So then, where
saying
should
I'm
I have
very,
found
very
out
surprised.
about this if it's so
So
surprising?
striped RAID is where you basically have the same information but split up on different volumes, so you have redundancy. So if it goes in it bad on this drive, it's still okay on this drive, so you can still recreate the data. Your data is not lost. So that's what kind of the idea that you're talking about with the redundancy in the strands of DNA is you have multiple different parts of it created at the same time. So, you know, if one strand goes bad, you can use all the others to compare against and still have a correct sequence.
In a very loose sense, they are both physical redundancies. Yes. So yes, they are. These are examples of physical redundancy. In this case, it's two drives. In the nucleotide, in the DNA case, it's multiple strands of that region of the DNA that were read at the end of reading all the DNA. And that region that encodes that part of the information would have been read by the sequencer like possibly 10 or more times. 10 is a low number. It's often, you want to go for like hundreds of times reading that, and you do statistics on that to see, well, we got most of those are the letter A, and then a couple are C's and one was a G. Well, since most of them are A's, then we can assume that that is actually an A at that spot, even though we got some errors there, technically. We can ignore them.
It's not like you have a copy of a copy of a copy for, in case this copy goes bad, we have this good one. You're taking like a comparison of like all these different copies you made and going, okay, which one, you know, how many of them are the same as the other ones, and we're going to go with this one.
Yeah, and that's just one method. That's like the simplest method kind of that they use. That's built
the only
into
method I know of.
No, that's like basically you doing that is something I've done in the lab. It's called PCR, when you make a bunch of copies of a gene, and it's just an elaborate form of PCR that they're doing that. And so that's not all that special. They have developed like a codec, like, you know, we talk about video and audio codecs and stuff. They've designed one of those for DNA, you know, to deal with errors in using bits, you know, for DNA. What's up? Is there noise in the background?
I heard music from somebody, I think.
No, I thought I heard a cat.
It's meowing cats in the background.
Yeah, I was like, I thought I heard a
You guys-
cat there for a second.
Out
I
of
was like,
everything, you heard the cat? She was in the
Yeah.
other room meowing.
I was waiting
No, my
for a
cats.
cat to come up because you had the
Oh.
cat the other night. I was
Yeah,
just
but
waiting for the cat to pop up, and then no cat came.
Was
And I
your
was like,
cat
oh.
meowing too, Scott?
Yes, it's feeding time.
Oh, okay. Because mine
Janelle
was
is
meowing,
feeding
and
them.
mine's a pain in the you-know-what, so.
Yeah.
She's scratching at
Very-
the door now.
So yeah, there are other methods that they are using to try to make the data more robust, and it's even in the encoding of the information itself that they are making it more robust. So they're being able to deal with error correction like that.
I would imagine there's a long way to go with this still. Yeah.
Yes.
I mean,
So it's important to put this into the proper context. Like, this is not something that's going to be used tomorrow or for this purpose. Like, technically it's being used now.
Yeah,
Actually,
not-
yeah,
it's
it
in
is
very
not in,
niche
like,
cases.
mainstream.
It's-
Yeah, no.
There are
but-
commercial applications, basically. But yeah.
No, like
Even
people,
that,
like,
it's like boutique, kind of, as it alluded to. It's not really
Yeah.
being used actually commercially effectively on a scale that I'm aware of. Like,
no, they bring it up for like people that do like time capsules and stuff or bigger projects. You know,
so
just trying to keep the data alive as long as possible.
they do all kinds of stuff. Like, there was one video on YouTube that like talked about this guy that had his Bitcoin passphrase stored in DNA. It was like his backup to a backup to a backup kind of thing. Just
If
in
he's
case.
got that much Bitcoin to where he needs to do
right.
that, then he's got plenty of money to go ahead and buy that shit.
Right.
Well, I mean, if you think about it, it's an insurance. You know, you're paying for insuring your information, and you know, getting DNA sequenced is actually not that expensive nowadays. Like, I think that guy mentioned like $1,000. I don't remember how much he said he paid, but like some cases you can pay like $50, you know, less than $100 for like a small fragment of your DNA. Be like, I want ATGC ATT. Send me that, and like $50. Yeah, like it's actually not that expensive. You'd be surprised. But
Sounds interesting. How do they provide it to you? I guess there would probably be different levels of purchase, right? I mean,
sure, yeah, there's different
either have it
providers.
stored in a site that's cryo freezing, or you could have it in your refrigerator.
Well, when they ship it, they'll often ship those kinds of things with cryo materials, so like ice packs and stuff, and like styrofoam and all. Like
Sure.
I've worked in a lab, and we have had to like receive things like this. And,
Yeah.
And then you just take it out and plug it into the port on your computer, and you can just read it, right?
Yeah.
Well, so I mean, there is something called nanopore sequencing, that's pretty neat if you wanted to look into that. That's not what this article was about, but like that is an example of how these technologies are improving and will continue improving, and can be a simple matter of plugging it into your USB port and sequencing some DNA. That is what Nanopore can do. They have like one model of their little like sequencers that you can actually plug into the USB slot. It's not the best of their models, like it's more error prone and this and that, but like you can do it, you know. Some people use it for like field studies. Like if you wanted to do some sequencing out in the field, you literally have your thumb drive based little like thing you plug into your computer and drop a little bit of DNA into the sensor, and like 15 minutes later you have sequence data.
So, but yeah, basically there are ways for, you know, normal people computers to read this stuff.
Yeah, you'd want to be aware of like the codec and the coding strategy they're using, like because there are different ways and it's not standardized at this point what A would mean, you know, digitally. This one company, they have their standard, like A is zero, the number is 00, and then T is 01 or C or something, and then G is 10, and then the other one is 11.
It's just the
Yeah.
conversion.
Well,
yeah.
We're a long way from taking basically a flash drive stick of DNA and being able to have all the world's music right at your fingertips.
Yeah.
So
Yeah.
not there yet, but
it's true. Long way to go for that, but it's
in that respect, for that kind of stuff, for you know, being able to play games and stuff, reading off of DNA, like we're that's not where we're going.
no, yeah, the kilobytes per second, you know, the rate would be really slow at this point. And it might always be like, that would probably be pretty difficult, but
I mean, this is just pure data storage.
yeah, it's archival. It's an archival storage solution. You could think of this as like being our pyramids at Giza for our like generation or epoch.
This
or era
is going
or
to
whatever.
lead to genetic memories.
You can
write your own genetics and your own learning. And
well, where it's
think of
going to go,
your child's fetus. That's
where it's going to go is the financial sector. It's where it's going to go.
I don't know. I don't really know.
We're going to do that, and then we're also going to get rid of all these massive server farms. So.
I'm sure there'll be like data like who the presidents were and like historical figures. We'll want to like store those probably in like DNA time capsule kinds of things up in the Arctic. Yeah. I could foresee.
Like I said, that's about the only like normal application of this stuff that I've seen is time capsules. I mean, I mentioned it 3 times already. It's like that's you know, just because it will last for a very long time given the right conditions,
and reading and writing
multiple thousands and whatever of years. So yeah, and then again, the whole worry of somebody unearthing it and not being able to read it is kind of a non-point. So that's what makes it so. It's like if you go in, like literally, if you dug up a time capsule tomorrow from like, you know, the 40s or something, like what are you going to do with any information you find in there? Like if there was any type of data storage or anything, like you wouldn't be able to read it. You'd have to go to a museum to find something.
I was gonna say, I'm sure there's still something working somewhere that would read it. Probably more than you would even realize in a lot of cases. But I still have a working VCR, but I don't ever use it.
Yeah, well, I mean, that's still more recent than some of this other stuff, you know, like the original computers that literally ran on freaking punch cards.
Yeah,
you know,
it's like what you're saying.
Yeah.
There are no wall computers left. They don't exist anymore. I understand. Yes.
Room computers.
Yeah. Mainframes the size of your car don't exist anymore.
Yeah. When's the last time you heard the term mainframe?
Well, I mean, we don't work on servers either, but
yeah.
You brought up an interesting point, Rob.
I'm sorry.
Sorry,
how dare you? Jeez.
Sorry, my mind went blank. What did you just say?
I didn't mean to.
What were you just talking about in more general terms?
About not having to worry about being able to read it, you know, thousands of years down the road. That, or the fact that if you went to go like dig up a time capsule from, you know, the 40s or something, whatever data storage medium they had, you probably would be hard pressed to find something that would read it. No.
I don't know. I don't know what I was thinking, but I
How
mean,
far back do I need to go here? I don't know.
No, I think that it was more recent than that. So it's just something you said triggered a thought, and you can't think of it now.
no, yeah, I got sidetracked by the cats and forgot what I was going to respond to. But
Damn pussies.
I mean, as far as the standards, like we kind of alluded to it, but like USB is not going to probably be around in a while, but DNA will be. And I guess I see your point. Like we won't necessarily know what the A codes to. You know, we might not know what standards were used if the A encoded to 00 or 01 and how to interpret that data. And we'll probably still be using like they might not be aware of ASCII, you know, the ASCII, like the standards of binary information into symbols. They might not be aware of that in the future. But like you said, that's kind of a non-issue because you can use cryptography techniques and programming to kind of brute force that to figure out and get a useful signal out of that data, I would think.
There's a lot that goes into storing it more than just having the DNA and putting it in a cold box, I think. But yeah.
You'd be surprised, actually. The cold, like, it can be, yes. And they are looking into like chemical ways and possibly even enzymes and things like that that can help store it more. But just good old fashioned cold is like the way to do it.
What I'm saying is they're not just going to store a piece of DNA with no record whatsoever of what's on it or, you know, anything like that, or how to read it or how to use it. These things are stored in facilities that are meant to keep these things that they can use to read them, I'm sure. I mean, it just doesn't make sense that they wouldn't be stored with an ability to read it.
But I mean, think
about hieroglyphics. Like, sorry, Rob.
No, go ahead.
I was just thinking like they might have tried to leave little like keys and legends and stuff to be like, these are what our hieroglyphics mean, but we might not have ever found those. Or even if we did, we might not have known how to interpret them. But yeah, eventually we have learned from like the whatever that tablet was and other sources like the Rosetta Stone. Like we've learned what these different symbols mean. You know, we've been able to decode them with surprisingly little information.
Yeah. I mean, it is possible that in the future, if they don't have the means, they can develop it also. I mean,
listen, and again, finding, you know, taking a SATA drive with a whole bunch of information about, you know, what happened, you know, now or in our time. Fast forward 300 freaking years. One, if you bury that drive somewhere, I don't care if you put it in a hermetically sealed box or whatever, without power, chances are that drive is going to be freaking unusable by the time somebody unearths it, right?
Exactly.
So far better chance of someone being able to read the data on this DNA storage than any medium that we have right now. That is in mainstream right now.
Sure.
So, but yeah, definitely not for keeping your porn on your computer. So that's not what it's for.
I wonder what the read-write durability of DNA is.
As far as like the error rates?
As far as how many times can you read and use the same sequence to rewrite? I mean, I don't know how it works.
Erase it and use the same strands to recopy information on it.
Literally like erase the strand and you get the A, C, G's, and T's back when you read it? Are you able to do that? I mean,
no. Like not that I know of anyway.
Yeah, like yes, you can definitely. Like I don't know where the misconception is here. So I want to work with you guys. Like if you have a little bit of DNA, making a lot of DNA out of that exact DNA, making a bunch of copies is trivial. I've done that hundreds of times. It's super easy if you have the right materials. You're
saying once you put information on to okay, term's going to be a little bit weird here, but you have like a flash drive, right? You can put information on it, you can delete information from it, and you can put more information in that same place again. I didn't think it worked that way with DNA.
Well, so you're talking about that would be like saying that that's not how transistors work. Well, because you're talking about the wrong thing. You know what I mean? Like you're talking about a whole working CPU not the transistors, but you're talking about like the bits and bobs that are DNA. But you could design a system where it's, and that's kind of what this is actually about. It's about a chip that they use that is a system that can do this really well. But you could have a more intact system that does handle all that, that's storing the DNA and all that, that is in like a little chip.
So you could literally write a sequence, erase it, and write a new sequence. In that
Yeah,
same
I'd imagine it'd be
if you will.
really hard, but I'm sure it could be done. Yeah, but to do it in like,
it's not click of a button, anything like, yeah.
None of
And
it's
I didn't
click
think
of a
it
button.
in the sense that we know it or we understand, you know, like deleting and or rewriting over, you know, using the same space or what, like it's not the same thing. Or that it would be really, really difficult to do so.
yeah, you can think of it like,
I mean, it would be better just to like grow more synthesized DNA and code to that. Like,
you could just take your sample that you're trying to read, because we're talking about after it's already been synthesized and we're just trying to read it. Yeah, just taking a little bit of that and doing PCR on that is really trivial. You can get a bunch of copies of it that way and thus have a lot more of that DNA to do stuff with. Yeah.
Reading DNA doesn't destroy it, does it?
No, but it kind of, I guess it could depend on the method you're using, but like the common, like I guess the point is it doesn't really matter, because if you have like a stock solution that has your DNA and it's got more than one copy of it in it, you only need like a little bit of that solution, and then you can make another vial with a bunch of copies of that. And so you'll never like run out of that DNA, because you can always keep making copies.
Do you not need to sample the full strand of DNA though? You just need like a small little piece of it to get the whole sequence. That's what I'm not, I guess, following.
So it's data. So this is like, if you want to get into all the data science, it's pretty complicated, but like you could take a single file that is like one file and chop that up into a bunch of sequences. But that's kind of getting into the weeds. I don't know if we want to go into like the weeds of.
I do kind of want to get into that, but I'm gonna. I was gonna say, yeah, I do, but I'm gonna go ahead and end it here because we're running up pretty high. That has been technically incorrect for today. Please like, comment, and subscribe. Let us know what you think. Really interesting stuff, and we're gonna keep going with this. But later.
A lot of fun.
Okay. I lost my mouse. Shit.